No. Is it okay?
So nice to see you. Thank you. Okay, I've got that one there. Yes, sir. Sorry, this is inside. They haven't really got the website.
How to get rid of this thing at the top? The battery is running low here. Yeah. I don't find my cursor.
You.
Picture. Is there definitely something over there with people?
Welcome to this public lecture. I'd like to request the speaker, Professor Seiberg, to come on stage, and I'd like to request our director, Professor Chenglur, to welcome him.
Oh, thank you. Thank you.
Okay, great. So our speaker today is Professor Nathan Seiberg from the Institute for Advanced Study, Princeton. Professor Seiberg did his PhD at the Weizmann Institute in Israel. He then moved on to a faculty position in the Weizmann Institute, and then a faculty position at Rutgers in the US, and then finally moved to his current faculty position, faculty position at the Institute for Advanced Study, Princeton. You know, that's the place where Einstein was. Okay, Professor Seiberg is an extremely eminent physicist. His contributions to physics have won him many, many awards. I'll just name a few of them. These awards include the Oscar Klein Medal, the MacArthur Fellowship Award, you know, this award that's sometimes called the Genius Award, the Danny Heinemann Prize of the American Physical Society, the Breakthrough Prize in Fundamental Physics, and the Dirac Medal of the International Center of Theoretical Physics. Okay. Professor Seiberg has contributed to many areas of theoretical physics and is perhaps best known for his work on dualities and supersymmetric theories. His famous Seiberg dualities and the related Seiberg-Witten dualities established that established somehow authoritatively in complicated systems that quantum field theories can sometimes, the same physical reality can have two different dual descriptions that look very different when you start out, but they describe the same they describe the same physics. This work of his, which was done in 1994, has had lasting impact. Hundreds of people now work on it. It's generated tens of thousands, maybe hundreds of thousands of papers. I think it's no exaggeration to say that Professor Seiberg is one of the most eminent living physicists, and we're very honored to have him lecture us. One small little personal note: Professor Seiberg is not just a great physicist, he was also my PhD advisor. And so I can say from personal experience that he is the best PhD advisor you could expect to have. Okay, so Nati.
Can you hear me? Can you hear me? So Shiraz was my graduate student and is the best graduate student one can hope. So first of all, I'd like to thank the organizers for inviting me to come here to India and to Mumbai. I've been to India a number of times, but this is the first time in Mumbai here, and I'm really excited about that. Really love India. It's fascinating. Physics-wise, India is a physics powerhouse, and the physicists here are among the world leaders. And for this reason, it's always fun to come here and talk to them and hear about their work and their research. I find it extremely inspiring. Turning to the talk, the title of the talk has a question. And I will address the question, what happens at shorter distances? But the main point of the talk is not the answer to the question, but the question itself. We will see that the question itself is much more interesting than the answer to the question. And although it sounds crazy, I hope by the end of the lecture, you will see exactly what I'm talking about. So I'm going to start from some very simple examples from everyday life, and I'll gradually make things a little bit more complicated. It's common in life and in the sciences, and in particular in physics, that we have different disciplines at different length scales. And let me demonstrate it in a simple example of cars. So this is the engine of the car. There's an engineer who designed the engine, and there might even be different kinds of engineers who specialize in different parts of the engine. And they put the engine together, and the engine works. Then they put it in a car, and the driver drives the car. Some of you have driver license. You know how to drive the car. You know how to manipulate the car in managing the traffic, keep the car in the lane, maybe stop it when necessary. But many of you, well, you guys are interested in physics, so maybe not you, but typical drivers have no idea how the engine works. There's no reason to know how the engine works because there's an interface between the driver and the engine, and we just need to know how to operate the interface. In fact, some of the engineers who built the engine and some of the mechanics who fix it when the engine breaks don't even have a driver license. So they don't know how to drive. So some people know how to drive, some people know how the engine works, and they're kind of separately together, and there is no need to know how the engine works in order to operate the car, and vice versa. Then at even longer distances, we have people who design the traffic. So there are bridges and roads, and they have to decide how many lanes to put in every road, and where to put a bridge or a tunnel, and where to have put traffic lights and all that. Many of these people don't have driver license, but they know how to design these things. Some of them are civil engineers who know how to build the road so that it won't collapse. Few of them actually know how the engine works. So we notice here that at different length scales, we have different disciplines, different expertise, and nobody has to be an expert in everything in order to work. Most of the details at one length scale are completely irrelevant to operate the other length scales. The engineer doesn't need to know how to drive, know how to build a bridge, and the urban planner who builds these roads doesn't even have to have a driver license. Let me give another example from another branch of life, which affected all of us recently, COVID-19. And we see again the same pattern of different disciplines at different length scales. At short distances, we have a virus. The virus is very small, a few tens of nanometers. That's more or less what the COVID-19 virus looks like. And the people who study it are virologists. And they look at it and they study the RNA and they develop a vaccine, and it's very exciting and it works. Vaccines do work, by the way. Might soon be illegal to say it, but at the moment it's still legal. Then at longer distances, we have people who decide how to keep the public safe. Should we wear masks or not? Should masks be mandatory? How many meters should we have between individuals? There's a public health question, and the people who study it are epidemiologists. Many of them do not know anything about the RNA of the virus. It's irrelevant for their decisions. They just need to know how the droplets spread from one person to another. Is it airborne or not? And these are different people who deal with the virus or the transmission. And going to longer length scale, we have the whole globe. There was a pandemic, and we needed to stop the pandemic from spreading. And there's a political question: should we close the borders or not? Should we let people travel from one country to another, and by doing that spread the disease or not? Maybe we should isolate them when they come. In fact, even in the middle case, for how long should people be isolated after they were infected? So we see here again the same thing, which will be a pattern through this talk, that at different length scales, we have different disciplines, and most of the details of one length scale are totally irrelevant for the discussion in the other length scales. So again, we saw that in the example of the car, about the different length scales, and we see it now here in the discussion of the pandemic. This is actually extremely common in science. So I gave examples in everyday life, but this is very, very common in science. In fact, most of science works that way. And it comes under the name of separation of scales. Nature has a hierarchical structure, and phenomena at one length scale are almost independent of all the details at other length scales. They're not completely independent, but most of the details are irrelevant. And we demonstrated it in the two examples of the car and COVID-19, and we'll see a few more examples later in the talk. So I put here the rulers, really emphasizing that whenever we study a phenomenon like that, the first thing we have to say is what length scale we are interested in. And then there's this peculiar thing that the story breaks into separate, almost independent stories, one at each length scale. So there's no need to understand simultaneously all the details at all length scales. We can study nature one scale at a time. No need to study all of them at once. In fact, we are extremely lucky that this is the case. because otherwise it would have been impossible to understand how nature works. See, the fact that we can study how we throw a ball from one person to another, or we can then study quantum mechanics at shorter distances, or we can study galaxies at longer distances, and we can focus on one length scale, study that, and kind of ignore the rest. This is an enormous simplification in the problem. Otherwise, we would not have figured it out. And honestly, I gotta say, it's very surprising that this is the case. And I have no idea why it is the case, because a priori, there is no reason why this should be the case. Why should it be so simple? We can say that nature is kind to us, because it didn't have to be so simple. Nature was kind to us that we have this thing that the problem breaks into littler, smaller problems that can be studied individually. In fact, Einstein has already said that subtle is the Lord, but malicious he is not. I'm not sure whether this is what he had in mind or not, but this really fits what we are saying here. Nature is subtle. It's extremely interesting, but it could have been much worse. Could have been much worse if we had to understand all scales at the same time. I want to give another example, which will be important later in the talk, the example of hydrodynamics. So the name of hydrodynamics, the word hydro, it comes from Greek, and it means water, and it describes and dynamics actually means power or force, and it describes the flow of water. This name was coined in the late 1700s, and it's being used not only for water, it's also being used when any fluid flows, like oil or others. And it's also used when gases flow, like air. And we'll see examples of that later. The equations that describe the flow of water were fully understood by the end of the 19th century. Yet, there's still very active line of research, mostly by mathematicians who study properties of these equations, and by engineers who say design airplanes or design a car, and they would like to make sure that the drag force that stops the car will be as small as possible. Also people who design ships. So we see here something interesting. The fundamental equation was understood already in the 19th century, but getting all the consequences takes centuries, and it will probably continue to take centuries as people find more and more interesting phenomena associated with various flows. So here is a typical example that we are interested in. We have waves in the ocean. So in here, we have water flowing, and in here we have air, and there's a surface separating them. Like a two-dimensional surface, it has ripples on it, because it's a little bit curved. These are the waves. And these equations of the 19th century tell us how the water flows. So there's pressure, and we press, and we can put an obstacle, and the water goes around the obstacle. And if we have wind up there, it affects the shape of the water, and we can get waves. And even if the wind stops, the waves keep going and leads to swell. So there's a very detailed story about how the water flows. And qualitatively, we understand it, but there's still a lot to learn from it. However, today we know that this is not the right story. It's not the right story because if we look very carefully at the water, there is no surface there, and there is no water and air separately. Instead, we have molecules. So if we look very closely here, I come very close to the screen. Actually, there is some granular structure also here, but that's not the one I'm talking about. So if we look at the water, we have molecules there, water molecules bouncing around. The general flow of the molecules is in the direction of the flow of the water, but some molecules go in the opposite direction. Some of them go up, some of them go down. They collide with each other. It's extremely complicated. The same is true up here when we discuss the air. Here we have oxygen molecules and nitrogen molecules. It's referred to them in general as air molecules. They're also bouncing around. They also collide. They also flow in different directions. And what about the surface of the water? The surface of the water that separates the air from the water. If we look at it very, very carefully, and I come very close to see, there is no surface there. We have more water molecules here and more air molecules here, but there is no clear separation where one of them ends and the other starts. Because there are water molecules which go up into the air, and there are air molecules which go into the water. And there is a region where they're kind of mixed, and below that, there's much more water, and above that, there's much more air. And when we look at it with full resolution, it seems to us that there is a surface separating the water from the air. But as a matter, if you look very carefully, this is not true. There is no surface there. So the idea of the surface is an approximation that those equations from the 19th century study. So the equation from the 19th century study the shape of the water, and even though there is no shape there is no surface. So there's an approximate notion of the surface that we all know what we're talking about. We look at the water, we see this is where the surface is. But if you look microscopically, you look at short distances, there is no surface there. Interestingly, if we wanted to solve the problem exactly, what we will have to do is to keep track of all the molecules of the water and all the molecules of the air. This would be completely intractable because there are lots and lots of molecules, and they move around in a very complicated way, and they collide with each other. It's extremely complicated. It's not practical. The approximation of these equations from the 19th century is extremely good because we don't need to worry about all these details at short distances. And if this story sounds similar to what I had in the previous examples, it's not a coincidence, because it's the same thing that happens again and again in science. We have an approximate description, which is extremely good. We refer to it as an effective description. And this effective description captures what's going on here. And that's what the engineers use when they design an airplane. They don't care that there are molecules there. In fact, if they cared about the molecules, they would never be able to solve any problem because there's so many molecules to keep track of. So this is actually quite common that we have different descriptions at different length scales. One of them is more accurate, but might not be practical. And the other one is more effective as it captures what we are really interested in and does not keep track of where all the molecules are, which is a detail we're not really interested in. So in philosophy, this idea is known as reductionism. The reductionism is a statement that we can explain what happens at long distances as a consequence of what happens at short distances. And we have, which is the ingredient, and we have separate descriptions at the two length scales. So over the past several centuries, science has progressed in a two-way approach. So element number one, remember, everything is broken into separate scales. We have separate disciplines, separate stories at different length scales. The second point that we'll learn here is about the two-way approach. First of all, we go to shorter and shorter distances to find a more complete description, a more accurate description, a more detailed description. So the more correct description is always at shorter distances, and we have an approximate description at longer distances. So this is like peeling an onion, as we have layers and layers of different disciplines, and we always find at shorter length scale a deeper story, a deeper understanding that gives rise to what we had before as an approximation at longer scales. At the same time, we also go outward. So I emphasize, this is a two-way approach. We have a two-way approach here. This is going inward to shorter distances, but we also go outward to longer length scales. We go to use the same laws of nature that we know at one length scale, and we use them to derive what happens at longer scales. And we do that for two reasons. One, to test that our understanding is right, but more exciting, we find new phenomena. Once we understand what's going on, we can use it to find new phenomena and even find technological applications. So we refer to the long distance description as an effective description. It's approximate, but effective. And I demonstrated that in the example of the waves in the water. We can discuss the law of the water without mentioning the molecules, and that's much more effective and much more useful. So continuing with this reductionism, progress happens in the two directions, both going inwards and going outward. As we go to shorter distances, we use a microscope to explore what's going on at shorter distances. And at the same time, we get more and more details, and we learn more and more detailed understanding at short distances. The second approach is going outwards. We use the known understanding at short distances, microscopic distances, to learn more about phenomena at long distances. And we want that both to test our understanding and to find new phenomena. These are the two things I said before. So let me summarize here what I view as the beauty of science. The beauty of science is we have simple underlying laws. As we go to shorter and shorter distances, the laws of nature are quite simple. At the same time, we succeed to find very rich phenomena, lots of complicated phenomena at long distances following from the simple rules at short distances. So there's rich and complicated consequences. And this line of research going inward and outwards are not independent, as I said before, and there's an interesting interplay between them. We can go outward, try and find new consequences, test it, it's not right, and we have to go back inward and fix the basic rules until things converge and we understand what's going on. And of course, there are technological applications. By understanding the basic laws of nature and understanding their consequences, we can find new materials with interesting properties. We can also find new devices. Most of the technology around us was really found following these rules of going inward, outwards, understanding how atoms work, and finding new materials. And I'll just talk about that in the coming slides. So I'm going to focus on two disciplines and compare them. One of them is condensed matter physics and chemistry. I lump them together. They're not quite the same, but for the purpose of this talk, let me lump them together. And I could also throw in material science as another aspect of it. So here we study properties of materials. And again, we have to tell you what happens at short distances and what happens at long distances. So at short distances, we have atoms. We now know that the atoms have a nucleus in the center with protons and neutrons, and we have electrons circling around it. This was understood early in the 20th century. The characteristic length scale is 10 to the minus 10 meters. This is 1/1 with 10 zeros after that. So these are tiny distances compared to everyday life, and these are gigantic distances compared with the distances I'll talk in the next few minutes. In the physics, the rules of physics here are more or less understood. These are the rules of quantum mechanics, which were understood about a century ago. In fact, I think there was a celebration here in India of 100 years of quantum mechanics a few weeks ago. So this was understood more than 100 years ago, about 100 years ago, although a lot of progress has been made since then. And then we go to long distances and we find huge, rich spectrum of phenomena, lots of materials with different properties. And materials can be soft or hard, they can have different colors, they might conduct electricity or not, they might conduct heat, and they can also have all sorts of other bizarre phenomena. And this is an activity that continues today and will probably continue for a very long time, that starting with the known laws of quantum mechanics and the structure of the atom, knowing these rules, new materials keep appearing with very bizarre properties, leading to new technologies that help our everyday life. But again, we see here these two length scales, short distances and long distances, and the relation between them. Let me move to the other discipline, that of high energy physics. High energy physics or particle physics. Here people study the basic matter particles, periodic particles of the universe, the forces that act between them. There's electromagnetism. This is a force we know from everyday life. But there's also a nuclear force that acts within the nucleus, and the weak nuclear force, which is responsible for various radioactive decays. And we have a rather detailed story, which works extremely well at distances larger than 10 to the minus 18 meters. Notice it's 8 orders of magnitude relative to the size of the atom. At this length scale, we more or less know what's going on. We know the laws of nature at this length scale, and we describe here various particles like electrons that everyone heard of, quarks, maybe some of you heard of, but there's also the Higgs boson and many others, and the forces acting on these particles. And as we go from 10 to the minus 18 meters, we can go to what we discussed earlier, these atoms and molecules, which are 10 to the minus 10. These are 8 orders of magnitude, which we completely understand. So that's very nice. We have a theory at this length scale, and another theory that follows from it at longer length scales. And then we can follow the previous slides that takes us all the way to everyday distances, new materials and their properties, etc. And that actually begs the question, what happens at shorter distances? If the story of chemistry and condensed matter physics describes everyday phenomena, new materials, as a consequence of the basic rules of nature at very short distances, and particle physics gives us a model here that leads to that as its effective theory, we can ask what happens at shorter distances that gives rise to the model of particle physics. And the answer is that we don't know. We don't know. I'll soon just tell you what we do in order to find out. But the answer is that we do not know what's happening there. And it will be extremely interesting to know the answer to this question. Maybe some of the young people in the audience will contribute to that activity. So it's still unknown, and we need better resolution. We need to look at shorter distances. We need a more powerful microscope, a microscope that will explore what's going on at these short distances. And this is what the microscope looks like. It's an accelerator. This one is the largest accelerator, the most powerful accelerator in the world. It's called the Large Hadron Collider. It's in the laboratory called CERN. It's outside Geneva. And they take protons, 2 protons, and let them collide with each other. And then they look at the debris that comes out of the collision. And based on that, they can tell what the laws of nature are at shorter and shorter distances. And there's discussion now finding another future collider, a more powerful machine that will explore nature at even shorter distances. This hasn't happened yet, and we hope it will happen. The other approach to explore what happens at short distances is to use the fact that our effective description is only approximate. It's not an exact description. We said it before in the example of the water. It's only approximate. So rather than going to shorter and shorter distances with better resolution, we can stay with the same distances, but measure things more accurately. So there's an ongoing activity to measure various phenomena at increasing accuracy, hoping that at some point there will be a discrepancy that would shed light on the rules of nature at these shorter distances. So let me review the phenomena we saw so far. We talked about condensed matter physics and high energy physics. These are 2 different disciplines which demonstrate this 2-way approach. The primary goal in condensed matter physics or in chemistry or in material science is to find new phenomena from the known laws of nature at distances of order 10 to the minus 10. We take as input what's going on at 10 to the minus 10 centimeters and meter, and we try to find out what happens at longer distances. In particle physics, we do the opposite. We know what's going on at 10 to the minus 18, and we try to go to shorter distances and find out what are the rules, what are the laws of nature, what are the rules at shorter distances. Surprisingly, these 2 different disciplines use very similar mathematical language, which is another puzzle. I do not know why this is the case. There's no good reason why this should be the case. I have some speculation, but I'm not going to say them here. In this context, I found a nice quote by Steve Weinberg. So Steve Weinberg was one of the pillars of 20th century physics, one of the greatest physicists of the 20th century. He was one of the architects of the standard model of particle physics, really a great man. And unfortunately, he died in the summer of 2021. But before his death, he wrote a paper that I found, which has what I find is a fantastic quote for the purpose of this talk. It's also fantastic on its own right. He says there is a school of philosophy of science associated in particular with the name of Thomas Kuhn that sees the development of science, particularly of physics, as a series of paradigm shifts in which our point of view changes so radically that we can barely understand the theories of earlier times. So this is more or less what I said before with one detail that I will soon emphasize. We have different length scales, and as we progress to shorter and shorter distances, our understanding changes, and Newtonian mechanics was abundant when we go to quantum mechanics. the old theory is replaced with a new one, which is much better. This is what the Thomas Kuhn approach is. And in particular, there was the standard model of particle physics that Steve Weinberg was one of its architects, which also kind of supersedes everything that has happened earlier. But then Weinberg continues and says, I don't believe it for a minute. I think our successful theories always survive, as Newtonian mechanics has, and as I'm sure the standard model will survive as approximations. This is essentially what I've been saying for the last half an hour or so. The old theory is not dead. The old theory is extremely powerful, extremely useful, but we have to remember that it operates at different length scales. So we see here in this quote, the two elements, different descriptions at different length scales. As we go deeper and deeper into matter, we find more correct and more fundamental description that gives rise to the old description as a consequence of it. But the old description is not wrong. It's still an approximation, and it is a useful approximation. And I'm very happy that this great man had this idea that I also agree with. So let me summarize the phenomena that we have seen so far and move forward. We discussed particle physics, 10 to the minus 18 meters. We more or less understand what's going on there. It works beautifully. There are still things, consequences that we have to work out, but I can view it as almost done. Then we have atoms and molecules at 10 to the minus 10. Here we know the rules very well, but there are still very interesting consequences that need to be understood. And then we go to matter around us, and every day new phenomena are discovered, both theoretically and experimentally, and they're extremely interesting. So there's a very lively activity connecting the known laws of quantum mechanics to matter around us. And I also put the surface of the water here as another example. And as we go to shorter distances, notice the structure of my slides is always, at the bottom of the slides, I have the longest distances of the slide. And as I go up, it's shorter and shorter distances. And as you can see, I left some room here at the top, soon be filled. Oh, I pulled my thunder. So there is another description, which we don't yet know what it is. A distance is smaller than 10 to the minus 18. And research is going on to find out what it is. And again, maybe one of you young people in the audience will give us the answer. What happens at this length scale? I know that some people in the audience are extremely interested in the answer to this question. I'm one of them, but I'm not in the audience. But we could be more ambitious and try to go all the way down to 10 to the minus 35 meters and discuss a topic known as string theory. And for the rest of the talk, I will be at the top of the slide. I will be here. And we'll try to be maximally ambitious. So what is this distance scale? This is where we face the biggest conceptual question in physics. It's the biggest conceptual question because there were two revolutions at the beginning of the 20th century. One of them was quantum mechanics, and the other was general relativity. Quantum mechanics explains how atoms work. In general relativity, this is Einstein's theory of relativity, explains the laws of gravity. So both of them, Newton was involved in the early stages, both in how bodies move and in how gravity operates. And at the beginning of the 20th century, these two ideas were kind of thrown out and replaced by more complete ideas. One is quantum mechanics and the other is general relativity of Einstein. Unfortunately, these two theories are not consistent with each other. And we have to put them together, and this is a big challenge. Interestingly, the length scale associated with that, so by now you should know, when you discuss a thing in physics, the first question is what length scale you're interested in, because the answer is different at different length scales. So what length scale? So this question was answered by Max Planck, and interestingly, he did that in the 19th century, which is completely shocking because in the 19th century, people did not know about quantum mechanics, they did not know about general relativity, and they did not know that you cannot put these two things together. These three obstacles did not stop him from getting the right answer. It's more than a century ago. It's really amazing that he did that. I have here the exact date. My memory is not as good as it used to be, 1899. So I think it still qualifies as 19th century. So in the 19th century, he calculated at what length scale that would be. And that's 10 to the minus 35 meters, or in terms of time, 10 to the minus 43 seconds. So 10 to the minus 35 meters is extremely short. We talked about short distances before. We said the atom is very small. And then we said that in particle physics, we're interested in distances which are far, far smaller than that. And then there was a problem, what happens at shorter distances? This is way, way very far. 10 to the minus 35 meters. And once this is understood, and this was already something that Max Planck knew in the 19th century, this will address the structure of the universe when it was 10 to the minus 43 seconds. This will basically give us the story of the origin of the universe. Or if you want to be theologist, I would say this is the story of creation. So answering the biggest question in physics, this is the one that Max Planck posed in one way or another, will really give us the story of creation, how the universe was created. So this is a challenge that we might take another century to address, but let me tell you where we are today and extract some lessons from that. So the leading candidate for that is string theory, and India is a powerhouse in string theory. Some of the leading string theorists in the world are here in India. India hosted some of the big string meetings, I think by now twice at least, twice, maybe there will be a third one, please do that. And it is an ambitious attempt to find a comprehensive theory of nature. And in what sense this is a comprehensive description is something I will soon say. It should describe the elementary particles. I talked about electrons, quarks, Higgs particle, and others, and the forces that act between them, like electromagnetism, the strong force, strong nuclear force, and the weak force, etc. But since Einstein's theory of relativity addresses the structure of space and time itself, not just the material that moves in it, not just the particles that move in it, it should also give us a story of what space and time mean, and I'll say a lot about that in the coming slides. One issue is that the theory faces enormous challenges. It's not an easy problem. For one thing, we do not yet have a complete description of the theory. We don't know what the underlying principles are. We do not know what are the basic equations that describe it. This doesn't stop us from doing calculations. We know quite a lot about the theory, but we do not yet have a coherent description of it, starting from the assumptions and then the consequences. The second issue is that we do not yet have direct experimental confirmation of the theory. And in physics, we need to confront theory with experiment. And we need that for two reasons. Number one, to make sure that the theory is right. Otherwise, we're just speculating. So that's one reason why we would like to have such experimental confirmation. But the second reason is that it would guide us in the search for the right ideas. Historically, physics was guided by experiment, and here we do not have this tool to help us. And it's not clear when this will happen, but it's clear why it is so hard. We are struggling in particle physics to get one or two more orders of magnitude, and this is many, many orders of magnitude far away. This is extremely short distances. Yet, it is extremely promising. It's extremely promising because the theory includes all the necessary ingredients to describe nature. It automatically has quantum mechanics. It automatically has gravity. In fact, it automatically has gravity in the form that Einstein described. And not only is it, we said earlier that you cannot put quantum mechanics and gravity together, here they come together in an automatic way. Both quantum mechanics and gravity are inevitable. This is an enormous success. We go from not being able to put these concepts together to a situation where the two concepts are inevitable. And they not only are they consistent with each other, they are inevitable. And it has all the forces and particles that we know and love. All of them kind of like these particles do exist there. So that looks pretty good. But in addition, string theory has led to many miraculous, surprising consistency. Especially given that we don't know what the fundamental rules are, of what are the principles that guide it, we're constantly surprised that the theory manages to be consistent. We calculate something two different ways, we get the same answer. This is a sign that we are doing something right. More interestingly, it passes a test of what I think is the best test for a deep theory. A deep theory in science in general is much better than what it was designed to do. You want to address one problem, you find the solution to the problem, but then you realize that the same solution solves also a dozen other problems that you didn't even know existed. Example, when Newton wanted to understand how bodies move, Newton invented calculus. Calculus is a deep idea. Why is it deep? Because it explains how body moves, but it's also very interesting in mathematics, and it underlies all of physics, and today it even underlies some ideas in social science. So that's clearly the hallmark of a deep topic. A deep idea works better than design, addresses questions that it was not even designed to address. And indeed, in string theory has led to many interesting connections between different branches of physics and mathematics, including the same hydrodynamics that I mentioned earlier in the talk, but also many others. It completely revolutionized some ideas in some branches of mathematics, led to new ideas and completely changed them. And it has all these unexpected implications. So all that sounds to me like this is a very deep idea that should be pursued, but on the other hand, the challenges are quite enormous. I'd like to move now to one aspect. I could give a whole talk just about string theory, but I'm going to focus on one aspect of it, which is connected to how I started the talk. Recall how I started. I said, what happens at shorter distances? And I said that we have to discuss different length scales, and once it's fundamental, we have a two-way street going from longer distances to shorter ones, and from shorter ones to longer ones. So let's discuss that in a little bit more detail. What is space? What do we mean by space? So we all have some intuitive understanding of space. We can go up or down or right or left, or we can go forwards or backwards. And we have some notion of distance, like these people here are closer to me than the people over there. So we have some intuitive picture of space. And we talked about the fact that we can measure distances with a ruler, or we can look at shorter distances using a microscope. Now, string theory provides a mechanism that makes space an emergent concept. This has a very long and interesting history. I'm not going to get into it, except to say that there is a way to make space an emergent concept. What do I mean by that? I mean that the notion of space is not fundamental and is only an approximate notion that operates at longer distances. Putting it this way, it sounds completely crazy. But in fact, earlier in the talk, we already had an example of exactly that. We had a situation where we saw a surface, and the surface looked pretty smooth, and we had equations that control the shape of the surface. But then we said, well, there isn't really a surface there. It only seems like there's a surface. There's an illusion of a surface. And there's a deeper understanding where there's no surface at all. There are molecules. So the surface of the water looks like a two-dimensional curved sheet. But looking closer, there's no clear surface. It's an approximate illusion. And the idea is that something like that should also be for space itself, the space that we know and live in, the space that we know and love. So the description of hydrodynamics in this case is an effective macroscopic theory controlling the shape of the surface. That's what I said earlier in the talk. What would be the analogy between this story that I had earlier in the talk and string theory? So this is the dictionary or the analogy. So the surface of the water is the emergent space. Hydrodynamics, which are the equations that describe how the water flows, that's, in our analogy, will be general relativity. The equations of general relativity describe the shape of space. That's fully understood. But the third line is what's really interesting here, is that in this analogy, the water and molecules that give us the correct description, but in which there is no surface for the water. This is the correct, more detailed description. That's the analogy in string theory. So string theory should give us the underlying description that does not have space as an input, and space comes out as an output. So we have a lot of reasons to believe that this is always the case, but it's not fully understood. So let us assume for the moment that this is indeed the case, and there is indeed such an emergent space. What does it mean? In the case of the water, it means that where does it break down? Well, the size of the molecule is, say, 10 to the minus 10. Maybe the molecule is a little bit bigger, 10 to the minus 11. Maybe there's a distance between them. the story of the molecules ceases to be relevant once we go to longer distances. And below that, there is no surface for the water. So what this means is that once we go below this length scale of Planck, 10 to the minus 35, once we go to shorter distances, the notion of space does not exist. There are no shorter distances. Just as we cannot ask, where is the shape of the water? Is it going this way or is it going that way? Between the molecules, the question doesn't mean anything. So the notion of space ceases to make sense there. And therefore, it's meaningless to ask, what are the laws of nature at shorter distances? We cannot measure it. That's why I put this red line on the ruler. Nor could we explore it. That's why I put the red line on the microscope. So we cannot explore nature at the shorter distances, and therefore we cannot even ask the question. We can ask, but it doesn't make any sense. What happens at shorter distances? So this is how I started the talk. What happens at shorter distances? Well, we can keep going until these distances, but then it stops. We cannot go further down. This brings me to the notion of time. Einstein's theory of relativity mixes space and time together. So if space is an approximate notion, maybe time is also an approximate notion. Let me go more slowly. So we all have some vague intuitive notion of time. Remember, for space, I said that we all have an intuitive notion of space. For time, we don't really understand what time means. Many philosophers spend a lot of time discussing this question. So we don't know what really it means, but we do have some vague notion, like this guy has been talking for way too long. So we have some intuitive notion, and physics is about time evolution. We describe how bodies move. We can also perform an experiment. We hypothesize what will happen, and then we perform the experiment, and then we know whether our prediction is correct or not. So we perform the experiment, and then we know whether we are right or wrong. We make the prediction before we make the experiment. In philosophy, this is known as causality. Also in physics, it's called as causality. The cause comes before the effect, not after the effect. They say that you cannot go back and kill your grandfather, called the grandfather paradox. So we do have some notion of time, and it's not clear what it means for time to be emergent. If time is an approximate notion, and it is emergent, as of today, for space, we have some ideas how it could be. As of today, nobody knows what it means to do that for time. So Einstein's theory of relativity mixes space and time, and therefore if space is emergent, the case is likely to be also for time. But that immediately leads to many questions. Suggests that the notion of time is not fundamental. It emerges as an approximate notion at long times. And here I put the red line on the hourglass to make sure that we can no longer measure times at these shorter distances. At these short times. It's meaningless to ask what happened before the universe was 10 to the minus 43 seconds old. So we cannot explore time at resolution which is better than 10 to the minus 43. As a matter of principle, we cannot, because time doesn't make sense at these short intervals. And therefore, we cannot even ask what happens before the universe was that old. So understanding how time emerges will also clarify the creation of the universe, because the notion of time did not make sense before creation. So we cannot ask what was before creation, and somehow it started. There was nothing before, because the word before didn't mean anything. When the universe was created, it was created with the time, and there was no before. So if space and time are indeed emergent, there's an ultimate shortest distance and ultimate shortest time, 10 to the minus 35 meters. And if this is indeed the case, the notion of space and time ceases to make sense. We can no longer ask what happens at shorter distances or at shorter times. This would be very interesting in the context of this talk. When I said that we keep going to shorter and shorter distances, I asked at the beginning of the talk, what happens at shorter distances? So we keep going to shorter and shorter distances, and then we stop. There are no shorter distances, and therefore we cannot ask what's the more fundamental theory at shorter distances. So this idea of reductionism, of constantly going to shorter and shorter distances as time evolves, kind of over the last several centuries, people went to shorter and shorter distances. This reductionist pursuit to find deeper truth that underlies the short distances this will come to an end. There is no deeper truth because there is no shorter distances. So when I said at the beginning of the talk, I will address the question of what happens at shorter distances, but I will also address the question. That's what I had in mind. The question itself is much more interesting than the details of what happens at shorter distances. So let me summarize. I think I'm almost out of time. Let me summarize what we said. We talked about separation of scales, this miraculous thing that nature can be studied one scale at a time. Nature, otherwise, it would have been impossible to understand nature, and nature is kind to us. So this is the fact that it separates, number one. Number two, as we go to shorter distances, we find deeper truth, which underlies all the phenomena that we had seen earlier at longer distances. And using this deeper truth, we can understand phenomena at long distances. This is this reductionism, and I put an appropriate picture here for this philosopher who thinks about reductionism. So this is the two-way street. So these are the three elements at the beginning of the talk. First, it breaks to pieces. That helps us. Second, we have this two-way approach. We go to shorter distances to find new truth, and we go to longer distances to find new consequences and to reduce a complicated problem with long distances to another one at short distances. Why did it stop? So nature didn't have to be so simple. And I would also pose the question of why is it so simple? Then we discuss phenomena at various length scales, and I'll introduce here length scales that we actually did not discuss just to make the slide more complete. At long distances, we can discuss cosmology, which describes the universe as a whole. And then we can describe at shorter distances astrophysics, which describes stars and the dynamics of stars and galaxies. And we can go to shorter distances, say here on Earth, and study geophysics, earthquakes, etc. And we can keep going down in distances. We can study various materials around us. We talked about atoms and molecules. We're going down to shorter and shorter distances. We have molecules on the left, atoms on the right. And we keep going down to shorter distances. We have the standard model of particle physics with its electrons, quarks, Higgs, etc. And then we should be able to go on. There's no obstacle, but we do not know what the next step is. Hopefully the money will be there and the talent of the young people will be there, and we'll figure out what's the next step is. I'm sure it will be exciting. That I can give you a money-back guarantee. And then at even shorter distances, we have quantum gravity and string theory. In this context, we said that space and time should be emergent, and we made the analogy with hydrodynamics and the shape of the water. And we said that if this turns out to be the case, this will be the end of reductionism. There will be no shorter distance and no deeper truth. So in a way, if we understand what's going on at these length scales, this will be the end. There will not be a deeper theory at shorter distances. There will not be bigger questions to address what happens at shorter distances. We can no longer ask what happens at shorter distances. So in a way, this will be an ultimate theory. This will be the ultimate theory that explains everything because there is no deeper truth at shorter distances. Yet, this will not be the end of science. Even if we achieve that, this would take another century. This will not be the end of science because I'm sure that there will be many new interesting phenomena that follow from the same basic laws. So even if we reach there and we know what the basic laws are, there would still be new phenomena. Explain life, we can explain all sorts of things, which in principle follow from the rules of physics that we understand, but there's a lot to study, and that would be extremely interesting. Therefore, I say thank you and stop.
Okay, so we can take a few questions.
Maybe it was very clear.
Hello. Hi, sir. Nice talk. Uh, okay, so if so we can ask some other questions at 10 raised to below 10 raised to minus 35 meter, like some other questions. I don't want to ask about the space and time, but can I ask any other questions?
I'm sorry, what do you want to ask?
Can we ask any other questions at that scale? Not the questions about the space and time, but is there any other?
Yeah, you can ask whatever you want. I'm not guaranteeing that I know the answer. Yeah, go ahead.
But you said that there is nothing exist. It means
Yes. Oh, okay. I understand. You're talking about in the context of string theory, the shortest distances that we can.
okay.
Yeah. So we're not there yet. In some special cases, we know what the rules are, and we see how space emerges. But these are very special cases. And there's a lot to calculate, a lot to understand. We basically understand what kind of equations we need to solve. And there could be interesting consequences of the equation. So there's a lot to do. But as far as going to shorter distances to ask ourselves, what are the basic rules? That I think we will understand.
Okay, thank you.
Thank you, sir. One small question is two parts rather. One, is there a relation between this 10 raised to 35 as distance and 10 raised to 43 for seconds for time that distance you have had?
The ratio between them is the speed of light. And I hope I got the numbers right.
And another small one continuation, the 10 raised to 35 that you have said, minus 35, does this remain constant with all levels of dimensions that we speak of with strings theory?
So the 10 to the minus 35 is what sets the basic scale of length. So you could set it to 1 and just measure all other distances relative to it. So it doesn't change.
Across all
So
higher
the
dimensions.
reason we give a number to it is that we have a definition of the meter as a measure of length. And I think this was the distance from the nose of some king to the end of his fingers. And we try to ask, how do we measure the basic length of the universe in terms of this distance from the nose of the king? I would say the logical thing is to ask the opposite question. What's the distance between the nose of the king and its finger in terms of the basic unit of physics? But that's not the way science evolved.
Thank you so much, sir.
Some phenomena where this notion of separation of scales breaks down.
Very interesting question. So so you ask a question of whether we have any example where the separation of scales breaks down. So first of all, in the context of gravity, it happens. And more recently, there will be some discussion in condensed matter physics where these things happen. And if you're really interested, I'm going to give a talk on exactly this thing. When is the talk? In 2 days? No, I think the day after tomorrow. The day after tomorrow, I'm going to give a colloquium on exactly that, where this separation of scale breaks down. I find this fascinating, but these are really, in the context of gravity, maybe we shouldn't be surprised because of what I said here, that there would be a basic length scale, and the separation of scale breaks down exactly in the way that points to the shortest length scale, which turns out to be 10 to the minus 35, give or take. In other cases, these are very esoteric phenomena, and it might be that that's a red herring, but I personally am very interested. Whenever something that is so ingrained into me breaks down, I feel almost personally offended. And I feel like, oh, I have to understand that. So I'll talk about that in 2 days. It will be a little bit more, it will be much more technical than this talk. But this was an excellent question.
More questions?
Yeah, I have a question. Yeah, hi, thanks. Thanks for the nice talk. So at some point, you said that the language of the physics at condensed matter scales and at very high energy scales is similar. And you said you have your own thoughts on it. Can you give us a little snippet of what you were?
Well,
referring to?
so a little bit more technically, this comes under the name of quantum field theory. And quantum field theory describes both particle physics, how particles collide and the interactions between them, and describes phenomena in condensed matter physics. And these two disciplines, they operate at totally different length scales. The motivation is completely different. And there are also many slight technical differences. But these two, for me, it's shocking that the same mathematical structure controls two totally distinct disciplines. And over the last century, when this thing was discovered, there's been a lot of cross-fertilization between the fields because people realize it's the same phenomena. And a large number of Nobel Prizes were given to people who took an idea from one discipline and just brought it to the other. I can give a long list of them. So I don't know why it is. So I don't know why nature breaks scale by scale. I don't know why it didn't have to be the case, but it does. And I do not know why this happens here, but that's a fact. So for me, I think that all of physics should be described by quantum field theory. This is the language of physics. These are just two examples of it, but that might be too ambitious.
So my question is that why is it so that it is meaningless to ask questions about length and time beyond Planck's scale and Planck's time? Because after all, we have a concept of zero, which is the lowest. So why we stop there?
Yeah, very good question. So I do not know how to really answer this question, except to tell you an analogy. So I gave the analogy of the surface of the water. And I can take a picture and say, okay, here is the surface. It's this is above and this is below the surface. But if I look very closely, there's no real sharp surface. There are molecules bouncing here and molecules bouncing here. And I cannot say if I have these molecules bouncing different, going up and down, is the surface going that way or maybe a little bit above, or maybe I should go around these molecules or below that one. And the fact is that there's no surface there. As you go there, there's no surface. So there's some region or some width above the water that below that it's definitely water. Above that it's basically air. And around this layer, and there's a layer with some width, but there's no sharp separation. So if you try to answer the question, where is the separation between the water and the air? And you try to look at distances much smaller than the size of the layer, say 100 times smaller, you can't tell, is it here or is it there? It's meaningless because there's no surface there.
Thank you, sir.
Hello. Just continuing with his question. Does it happen that it's because that we are the observer and we are ourselves limiting ourselves to the development of the string theory in that context?
Well, I can interpret your question several different ways. One of them, we live in the universe, so we are the observer who observes the universe, but we're also part of the universe. This is a very good question that needs to be addressed, but it should be addressed if we try to study the universe as a whole. Our belief or understanding is that we can separate ourselves from the rest of the universe and still make predictions and still test them. And this has been working very well so far, and there's no reason to believe that it would stop. Now, maybe there would be a conceptual revolution, just as quantum mechanics was a conceptual revolution, and the measurement affects the outcome of the experiment. This is one of the consequences of quantum mechanics. And maybe there's something like this also at the Planck scale, but this is really hard to imagine because the fact that we are here, or even we have a brain and we have neurons in the brain, it's not at the same length scale. Why should it affect anything in these shorter distances? So I don't believe this is going to be the case. I believe that there is maybe one of you guys will come up with a very simple equation, which would look extremely surprising. It will be hard to understand, but it will be relatively simple, which will be operating at shorter distances, and it does not have space built into it. And if we just play with it enough, there's something that looks like space, just like the surface of the water. And the observer will play no role in that discussion. That's my belief. And I do not know if this will happen tomorrow. or in 5 years, or in 100 years. But I'm sure that this is the way things will progress.
Thank you.
So we have been attending the talk on string theory. Like at present, we have only theoretical ideas. So being in an experimental department, what suggestion would you give to us?
To experimentalists,
Yes. Like what sort
I
of?
wouldn't say wait until this is resolved, because that won't help.
But that may take a longer time.
That might take a long time, but nobody said it would be easy. On the other hand, I can very well imagine that somebody would come up with a suggestion that if we look at the sky somewhere, there are various stars that do something peculiar that really shed light on what's going on at very short distances. I don't see how this would happen, but I wouldn't rule it out. So we just have to be more creative and look for ideas how to do things. Many experimental things over the years were considered impossible until they were done. And in hindsight, it always looks easy. But so the same thing might be true here. So the challenge is really huge, but the payoff is also huge. You know, if anybody comes up with an experiment that proves string theory is right, it would be enormous achievement. It would be really an enormous achievement. I should also say that some of the implications of string theory, that it inspired ideas in mathematics or in other branches of physics, they were tested experimentally. So there are experimental tests in other disciplines of physics of ideas that were stimulated by string theory, both in condensed matter physics, plasma physics, and others. And they were tested experimentally. And the ideas in math that were inspired by string theory completely revolutionized some branches of math, especially in topology. So that's a success already. So even if you discard everything else, that's already a success. But when we have success, we just want to be more ambitious and do the whole thing. And how that would happen experimentally, I have no idea.
Fingers crossed for that.
Maybe two more questions.
Yeah. So actually, when you talk about, so you talked about Planck's scale, right? Planck's length and time, right? So those are two physical quantities, fundamental physical. Why don't you talk about mass generally, like because Planck's mass?
Yeah. So okay, maybe I should tell you what Planck actually did. Planck did not know about quantum mechanics. He did not know about general relativity. What Planck knew was one number in units of angular momentum that he found, known as the Planck constant. And then you realize that if you ask yourself, what kind of quantities can we form that have dimensionless, that are dimensionless? He didn't even know that this constant, today known as Planck's constant, has anything to do with quantum mechanics. Quantum mechanics had not even existed at that time. So he asked himself, what should we need? So with the speed of light that had already been measured, so he said, let's use units that the speed of light is 1, that's clearly fundamental. And let's set units where Planck's constant is 1, because there's a basic phenomenon that is associated with this number. So let's pick this as the units rather than the distance from the nose to the end of the finger of the king. And let's use these units. And then we just need one more unit, say mass. So in modern terms, I would say mass is related to energy through E equals mc squared. Length is also related to that. Time is also related to that, using the speed of light and Planck's constant. So we just have one more number to determine, and that's the calculation he did. It was extremely insightful, extremely insightful. He took numbers that were known, and he produced a more fundamental number out of it.
And what about charge?
Charge is, the right unit is 1. So there's no other dimension for quantity. Electric charge in the fundamental units is 1. So if you go through all of classical physics and quantum physics, you can write everything in units where the speed of, so this is like a measure. Instead of using meters, you can use units where the speed of light is 1 and Planck's constant is 1. And then you just need to supply one more number, which would be the Planck scale, which you can also set to 1, and then there are no other units, no arbitrary units. Everything else is determined in terms of these. Right. So the fine structure constant, which was measured at the time, is really 1 in the same unit because it's the electric charge square over over Planck's constant times the speed of light. That's the number that is measured. So in the end of the day, charge can be taken to be 1, which is the charge of the electron. The charge of the electron is 1, or precisely it's -1. So the charge of the electron is 1 rather than something in Coulomb's units. And they set the speed of light to 1, set Planck's constant to 1, and then there's one more thing that you need, one more unit that you need. And from these units, you can define pressure, height, electric current, voltage, strength of magnetic field, not measure it in Tesla or in other things, like everything follows from these basic units. And that was the point of Planck in 1899. It's quite an incredibly deep idea that he did that. He was really a smart guy.
Okay. So the length scale of the standard model and that of the like Planck scale, there's a huge gap, right? So is it reasonable to expect that some new physics might exist between that?
I'm sure there's a lot of physics, and I denoted it by a question mark. There's a lot of interesting physics until we reach the standard model of particle physics. Almost every order of magnitude, there was a new phenomenon. Sometimes we skipped 1 or 2, both going inwards and going outwards. Every few orders of magnitude, there's a new phenomenon, and the rules completely change. There's no reason to believe that this pattern changes where we are today in 2025, limited by our technology. So I believe that there are new layers of complexity with new principles, going all the way down to 10 to the minus 35. But the message of this talk is that there it will stop. Sorry?
Saying that the Planck scale, that's a very precise number. Like, why exactly is it so small?
Well, it's not small, it's 1. The other numbers are so
As in
big.
like the other, compared to the other numbers.
And the question you're really asking is, why is the universe so big compared to the natural scale? This is an extremely, extremely interesting question, and it comes under the name of the cosmological constant. And there are lots of ideas how to address that. It will be a topic for another question, and another talk. And there are various ideas. Some people in the audience know about that more than I do. I think it's fair to say that there is not yet a definitive answer on this question. Why is the universe so big? Compared to this Planck scale, which is 1. So the question is not why it is so small. That is 1. The question is why the other one is so big.
Okay, maybe I can end off with a question of my own. Nati, if time is emergent, then presumably quantum mechanics is also emergent, is also approximate, since quantum mechanics requires time. Have we seen any indication of this, or any suggestions for how this might work?
No, I'm totally baffled by it. But once the answer will be found, it will be obvious. And I can promise you, say, oh, why didn't I think about that?
Okay, so let's thank Nati again for a fantastic talk. People really seem to engage.